Okay, and you should also know that the moment is defined as the sum of the moments of all the forces in the system and all the couples that you have in the system. Well, you can, well, in a sense, they are not really different, but we actually show a couple at a point by this notation. It is usually equivalent to two forces with equal magnitude and opposite direction. And so if you have the distance d between these two forces, then m is equal to fd. And well, because the resultant of the forces are zero, we don't usually show the forces, and instead we just show the resultant moment, which is equal to fd, and we call it a couple. Okay, and well, when you have a system, you have imagine you have a body that some external forces are exerting on it at different points. Then you can have an equivalent force couple at any point in this system. For example, if you wanted at point O, then you first determine the resultant of all these forces. For example, here, if it is in 2D case, it would be sigma f of x and sigma f of y for the resultant in x direction and y direction. And then you're going to calculate the moment about point O, and then you will get the moment about point O. So then you can transfer, well, you can put the resultant force at point O, and that moment you got from all these forces at the same point. So this would be equivalent to this system. And well, the in the definition, the equivalent force couple can be defined at any point. So you can change the position of R, and then actually you can calculate the distance that R could have with respect to O that would exert the same moment that we had here. So you can change the position of R at a point, then you could have a system without any moments. So actually, imagine at first you have a system with several forces, and then you want to calculate the resultant of these forces and the position of the resultant of these forces at a point that there is no moment in the system. So then you first calculate the resultant, calculate the moment about one point, and then displace that resultant force in such a way that the distance would be equal to m over the magnitude of that force. So this is what we call the force couple, the equivalent force couple. In the first question, you have 260 pound force that is applied at point A on a beam section, and you're asked to replace this force with an equivalent force couple at center C. So based on what I said, the first what we need to do is to calculate the actually, well, we have just one force here, but you should decompose this force into x and y direction, and then calculate the moment about point C, and then you can get the equivalent force couple. So this is what we're going to do. Well, first you have to calculate the sine of alpha and cosine of alpha to get the component of this force along x direction and y direction. So you can, based on the geometry, you can calculate the length of AB, which is equal to square root of 2.5 squared plus this side, which is 6 inch, because this is the from here, from the top wing to C, it is 4 inch, and from C to B it would be 2 inch. So you're going to have AB 6.5 inches. And then you can have sine of alpha 2.5. Here alpha is this angle, 2.5 over 6.5. And cosine of alpha is 6 over 6.5. So you're going to have F as the summation of two components in x and y direction, which would be minus 260 pounds times sine of alpha, and well, you can get the signs by just watching the force. It is in the minus x direction and minus y direction, so both components are negative. So then you would have the vector, the force vector, by calculating the components of it, and then you can calculate the moments of this force by the cross product rule, which was the distance vector cross force vector. And the distance vector from A to C is 2.5 in x direction and 4 inches in y direction. And you can calculate the cross product based on this equation, and then you're going to have a moment about point C, which is actually the axis that comes out of the plane. If it is x and it is y, then you're going to have z plus in out of the plane. So the moment would be 400k minus 600k, which is actually let me see. Okay, you can expand this cross product as, let's write it here. 2.5 I plus 4J. So you can write 2.5 minus 100 if you expand this equation, and then you're going to have I cross I, which is 0 based on the cross product rule, and then you're going to have plus 2.5 minus 240 ij, and then you're going to have 4 times minus 100 ji, and then the last equation would be for j cross j. So the first and the last terms are 0. Ij is equal to I cross j is equal to k, and j cross I is equal to minus k. So you're going to have minus 600. This product would be 600, and then this one is minus 400, and you have minus k, so you would have 400k minus 600k, and this is the resultant of the last equation, minus 200 pound-inch. So this is going to be clockwise, and this is this has a negative sign, so it makes sense. Is there any question? All right. Okay, in the next question, we have a machine component that is subjected to several forces and couples in the system. You can see it in the figure. And well, all these forces have a resultant force and a moment around any point in the space. So we have a known force here, P, that in the question it is said that imagine it is 0. So we can eliminate this force, and then you can have a hole in this component, in this machine, that can stand the force, but not the moment. So the machine component can rotate around that point, but you can't change the position by exerting force on it. So if this is going to be in static case, then you have to put a hole in a place that there is no moment about that point. So well, imagine that point is either on FG line or GH line, and we're going to calculate the location of that point. So it is obvious that you first need to calculate the resultant in X and Y direction, and then you can take a point, any point in the system, and calculate the moment around that point. And when you calculated that moment, imagine that's the moment you're calculating. This is the resultant force, and also you have a moment. So you need to find a location for a point that there's no moment. So then you have to make a force couple equivalence system that has a distance d from the origin, and this d is equal to m over r. So if you actually place a rivet at this point, then you do not have any moment at this point, and you just have force. So you can make this component stable. We're going to find that point, well, which is by default on line FG or GA. So we're going to calculate the location of 2 points here. Is the question clear? All right. Well, let's calculate the resultant of these two forces in x and y direction. Well, this is x direction and this is y. And well, you have to calculate the resultant for three forces. Well, for a 200 Newton case, you have 15-degree angle with respect to the x direction. So, and it is in the positive direction. So you're going to have 200 cosine of 15. And you have for this force minus 120 cosine of 70, because it is in the negative x direction. Plus p, well, here p is 0, but it is still kept in here. So the resultant of force in x direction would be 152 Newton. And the resultant of the forces in the y direction would be minus 200 sine of 50, because it is in the minus y direction. And you have for this force minus 120 sine of 70 minus 80. Well, this is in the y direction, so we did not have any component in the x direction for this force. And you get the resultant of force in the y direction. So let's calculate the moment of these three forces with respect to point G. So you can calculate the moment of force around any point, and as I said, then you can displace that resultant with the distance that would be equal to the moment over the resultant force. So it doesn't really matter, but we for convenience we choose G here, because at the end we are going to calculate the position of point in FG and GA. So this is the best. Actually, this is the best. This is the best point to calculate the moment around. Well, we can, for example, we can calculate the moment around a point like G prime here. But then if you want to, for example, imagine the resultant of the force is something like this, and then you want to and you have also a moment, then you want to find a position here such that this D would be equal to M over R. So this is going to be hard because it is not easy to calculate a proper D here. But if you choose G, then you're going to have the resultant like this, and then you can change the position and get the let's discuss it through the problem. So first we calculate the moment around point G, and well, each of the components, for example, for the 200 case, actually the X component has the distance of 520 minus 50 millimeter. So then it would be 400. The distance between this point and G would be 470 millimeter. In meter would be 0.47 meter. And this is for the X component of this force, 200 Newton. And then for the Y component, this is the distance, which is indicated here. This is 50 millimeter. So it would be 0.05 meter, and 200 Newton times sine of 15. Well, this is the first line is related to the 200 Newton force. The second line is related to 120. Again, for the X component, you have the same distance as the X component of the first force, so it would be 0.45, 47. And for the Y direction, you're going to have what is the distance? It would be 240 minus this from A to G minus 50, which is 190 millimeter, right? This is actually this distance, which would be 240 minus this part. And this is the moment for the Y component of the second force. And for the last one, you're going to have, for P, you're going to have 180 minus 50, which leads to 0.13 meter for force P. And then for this 80 Newton force, you're going to have, this is the distance from A to C, 640 millimeter. So you should subtract 50 millimeter and you'll get 0.59. And you have also two couples, 42 and 40, and they are counterclockwise. So actually the sign would be positive, and you're going to get the resultant of a moment around point G. Okay, this part is wrong here. So then we want to find the location of a point. Well, so far we have derived the resultant of two forces in a resultant of these four forces: 200 Newton force at E, 120 Newton force at D, 80 Newton at C, and a P at point C. So the resultant in X and Y direction, we derive these two, and also we have a moment around point G. And so now we have an equivalent system. Actually, we have calculated the resultant of force. Imagine this is point G, and you have something like this. This is R, which now we have the components R of X and R of Y. And also we have a moment, mg. So now we want to find a point in space such that if we put that force at that point, there would be no moment in the system. So first we're going to do this on the FG line. And well, this is, imagine y is in the direction of FG, then you want to displace these two resultants, R of X and R of Y, in such a way that the distance D would be equal to M over R of X. Well, this should be originally D is equal to M over R, but here R of Y is not exerting any moment around point G. So this is just R of X. So to calculate the distance, you have to divide the moments about point G over the resultant of force in the X direction. So this is what we have done here. You have minus 55.54 Newton meter is equal to minus B 152. So well, we put P equal to 0 here. So mg would be equal to minus 55.54. And then R of X here is going to exert a clockwise moment. So it should, the resultant moment should be negative. So we have a negative here. And B could be derived as 0.365 meter. And on the GH line, so we're going to displace the resultant force over here. So this time, well, let's call it D1. And this is D2. So this time D2 is equal to M over R of Y, because R of X is not exerting any moment. So again, this would be clockwise, and you're going to have a minus sign here. So A would be 0.227 meter. Okay, any question? Everything's clear? All right. Okay, in A and B, uh, you mean the point that we calculated the location? All right, then. Well, D1 here is the distance from point G to point A. So this is something over here. Okay, this would be A, and B would be on the line GH. This is B. Any other questions? So let's review this problem. We have four forces and two couples acting on this system. So we're not going to be concerned about this P here. It is equal to 0. But, well, it is asked to calculate the position on FG line and GH line uh, for a rivet that cannot stand moment, but it just can stand force. So you have to find a location of the resultant of these forces and moments, such that there would be no moment on that point. So, well, we started by calculating the resultant of the forces in x direction and y direction, and then we calculated the moment around point G, and you should not forget to add the couples in the system, and then we derived a moment for point G. So now we have resulting in x, in y, and the moment around point G. So if you want so this is point G, we have a resultant force. Well, it is positive in x direction and negative in y direction, right? And then you want to find a point in the y direction in the figure I've drawn here, and so such that there would be no moment. If you put the resultant of the forces on that point, there would be no moment around that point. So you have to find D1 here, which is equal to m over r of x, because r of y is not exerting any moments right around point G. So this is actually mg. So this would be the equivalent force coupled system. So you have derived r of x and r of y, and we can easily derive d1 and d2. Is that clear? Okay. Well, we have a machine component, and we have two forces at point B, and one force at point D, and one force at point E. So we want to derive the equivalent force coupled system at point A. So it means we have to first calculate the resultant of the forces in here X, Y, and Z direction, and then calculate the moment these forces exert around point A. So then we are actually done. So the resultant of the forces, well, this is a 3D problem, so it is better to write everything in XYZ component. So here you do not have any oblique forces here, so you just have to actually choose a good coordinate system. So if you choose AB along X direction and Z along BD direction, then the 300 Newton force is in the X direction, which would be minus 300 Newton I, 50 Newton in minus 50 Newton in the Y direction, minus 250 Newton in the Z direction, and minus 120 Newton in the X direction. So we can easily calculate the resultant of these forces. And then in order to calculate the moment around point A, you have to have the distance vectors AB, AD, and AE, which are the distances to the point that these forces are exerting on. So R of B, based on the geometry, is equal to 0.2 meter in X direction. R of D is equal to 0.2 meter in X direction and 0.16 meter in Z direction. And R of E is equal to 0.2 meter in X direction, right? Minus yeah, this is where we have 100 millimeter here, so it would be minus 0.1 meter in the y direction and 0.16 meter in the Z direction. Okay, so we had M is equal to R cross F, so the total M would be R1 F1 plus R2 times F2, etc. So here, well, we have same distance vector. Someone had a question. All right. Are you talking about the previous question? I will go back to that after this is finished. Okay. So you have same distance vector for these two forces, 50 Newton and 300 Newton. So you can put it as a prefactor here, and you can say R of B cross these two forces and plus R of D for the force exerting on point D, and R of E for the point exerting at point E. So you have to calculate these three cross products, and then it is done. So let's go back to well, you have to talk to your professor about that. Okay. Well, this is A is the length from G to a point in on the FG line, and B is the length from G to a point on GH line. What do you mean by the axis? I mean, this is not the axis, this is the length of a line. Did I answer your question, Julian? Okay. Well, for the left side, it is obvious. We calculated the moment around point G and it was negative, right? It was negative because P here is 0. For the right side, uh, it is actually the resultant force is something like this. It is positive in the x direction and negative in the y direction. So you're going to have for in line FG, you're going to have R of x, which would exert a clockwise moment around point G, right? This is a positive R of x force, and it is going to be clockwise. That is why it is there's a negative here because it is clockwise. And same goes for the part B. Okay, yeah. Is it clear now why you have negative signs in part A and B? All right. And for part B, then you have Ry in the negative y direction, so it is exerting a clockwise moment around point G, so it should be a negative moment. Well, in 2D case, when you want to calculate a moment around, imagine point O, for example, and you have force here, and if it's G, then the moment would be F D, and D is the actually the smallest length from point O to F, which is the perpendicular distance from point O to vector F. What angle? Cosine of 15. 0.47. Where is 0.47? That's the length. That's the length of the x component of 200 Newton, right? Well, you have to calculate the distance from E to G. Then from E to A, you have 520 millimeter, and you have to subtract, actually, you have to subtract this distance, 550 millimeter. So you would get 400 70 millimeter, which is equal to 0.47 meter. Is that clear? So it is actually this distance. Which is equal to minus 50. For the y direction, from E to G, the y would be this, right? So it is 50 millimeter. D is on the line A. No, it is not on the line AE. You have a 50 millimeter distance in X direction from line AE. G is, well, it is actually 50 millimeter in X direction from A and also 50 millimeter in Y from A. Is that clear? This is the angle. This is 15 degree is the angle between 200 Newton force and X direction. This has nothing to do with the distances. The distances are between points A and E in X and Y direction. When you want to calculate the moment, then you have a force here at point E, right? You have here point G. Then this is the resultant of two vectors, right? E of X and E of Y. Then the resultant of the moment would be Ex dx plus Ey dy, right? So this is dx, and well, I did not draw a good picture, but this would be dy. Imagine this is point E. How about that? Yes. So what's the question? You have point G here. No. Okay. You have point G, and you have point E, right? So you have a distance here let's call it dx, and you have distance dy, right? This is the diagonal. Dx and dy are the components in x and y direction. You have a 200 Newton force here, right? It's really hard to work on this whiteboard here. And so let me go back to the slide. Okay. 200 Newton, point E, and you have point G. And this is on the diagonal, right? So you have dx and you have dy. Then this 200 Newton force has a component, let's call it ex and ey, right? This ex is exerting a moment, let's call it mx, of magnitude ex dy, right? This is the distance between force ex and g dy, and this is the magnitude of that force. All right, and you have my, which is equal to ey dx. Okay, then you have e cosine 50 dy, and here you have e sine 15 dx. Clear? This is cosine. Yes, otherwise, then if you want to calculate the moment directly, then you have to, this is your vector, right? Then you have to calculate this distance, right? So it would be easier to first decompose that force in x and y direction, and because you in the geometry that you have here, you have the length in the y and x direction. You do not have the distance in this direction, right? This is the d that this moment is exerting. This force is the distance this force has from point G, right? But so it is best to first decompose the forces, right? To ex and ey, and then calculate the moment and then add them up. So sigma m is equal to mx plus my in this case for this force. Okay. Any more questions? Sure. All right. Have a nice day.